Hi there, welcome to part 2 of chapter 6, where we're going to understand about transformations of random variables, and as well as what happens when we combine random variables, whether it's a sum or a difference. So here's some of your learning objectives for this chapter, this section. And in the previous video, we understood how to calculate mean and how to calculate standard deviation. And we learned that it wasn't just as simple as calculating an average or calculating standard deviation. We actually had to use a series or a sum of sequences. So how does that affect transformations? And if we recall from, I think, chapter 2, we learned about maybe chapter 4. Anyway, but we learned about transformations. We learned that addition and subtraction could affect your center, but it didn't affect the spread or the shape. We learned multiplication and division affected both the center and the spread, but it never affected the shape. And then you learned about z-score transformations, creating a mean of 0 and a z-score of 1 with all of your data set. However, with this, we're just going to look at addition, subtraction, and multiplication and division. So what happens when we add and subtract a constant to every observation? We realize, again, that we're changing center. Today, we're going to use that to change our mean. And when we are multiplying and dividing, we're also changing center, or the mean for today's information. And we're also changing spread. And in this, it will be our standard deviation. I need a new color. Okay. All right. So it does not change the shape. So let's just dive on in. What happens when I am multiplying a random variable? So this is a transformation, and we already know that in order to multiply, it's going to transform both the center and the spread. So be aware that that is what's happening, and let's prove it to ourselves. I think yellow will be visible. Okay, so we're given information about Pete and his Jeep tours. So Pete charges, this is on page 365 of the textbook, but this is just kind of a wrap up right here. Pete charges a certain amount of money for his passengers, and he also has a certain number of people on his trip. And so he goes between 2 passengers and 6 passengers. So it can have 2, 3, 4, 5, or 6. First of all, this is definitely discrete because you're not going to have between 2 and 3 passengers, between 3 and 4, et cetera, et cetera. You're going to have 2 passengers or 3 or 4 or 5 or 6. So he creates this probability based off of defining X as the number of passengers. We calculated the mean and the standard deviation separately, and we found that the mean was 3.75 and the standard deviation is 1.09. But if I also recognize that Pete is charging $150 per person, if I define a new random variable as random variable C, and define that as the amount of money that Pete collects on any randomly selected day, then we can create a new table of values that's provided in the reddish, orangish color. So again, what was I doing to 2 passengers to get this 300? I did 2 times $150, or 3 times $150. So this is a multiplication or division transformation. So what do I know will happen? Well, the mean will change, and so will the standard deviation. And if I very quickly do 3.75 times 150, and I do 1.090 times 150, I'll get some values. And if you do that for yourself, I want you to pause the video and put that in your cell phone calculator or a really quick calculator. What are those numbers? What's $3.75 times 150, and what's 1.090 times 150? Well, guess what? When I go ahead and calculate the mean and standard deviation of this data set right here, we end up with these values. And if you recognize these numbers, that's because you paused and multiplied and you realized 3.75 times 150 is 562.50. 1.09 times 150 is 163.50. So again, there's proof that the transformation can be done using that definition that I can just multiply by that constant B. And in this case, it was 150. So how do I compare the shape, center, and spread, or how do I cuss for these 2 probabilities? Okay, so the center of if we're talking about X, the center is a mean of 3.75. There are no unusuals. The spread is a standard deviation of 1.090, and the shape is approximately symmetric. How would I describe the shape center spread? How would I compare or describe? Then I would talk about versus C. The mean of X is 3.75 and the mean of C is 5.6250, et cetera, et cetera. So you would definitely cuss this out when it asks you to describe or compare. So here's just a wrap up of how we did that, how we multiplied. So this is the same information we saw, but there's another wrap up screen for you if you need it. Let's move on. So we've talked about multiplication and division. What happens when I'm adding or subtracting a constant? So again, we're talking about Pete's Jeep tour. We're just looking at his C value. If he collected that $150 per passenger, so we're looking at his C, his total collected value. We already calculated the mean and standard deviation. But what happens if we realize that Pete actually is, it costs him $100 per trip to run his trip, and so we have to subtract by 100 each time. Well, what do we know about addition subtraction? What can it affect? It can affect the center, but it will not affect the spread, and nothing ever affects the shape, at least as far as we know. So we're not going to look at we're not going to look at spread or shape. So I'm going to assume that my standard deviation stays the same. And the only thing I'm going to do is change the mean, and I'm going to subtract by 100. So I'm going to assume that this mean is 462.50, and its standard deviation did not change, and it's still going to be 163.50, I think. So these are my assumptions, and let's check using the actual math, and ta-da, there it is. Here is proof. Again, we could cuss it out. We could describe and compare, because that's what this is asking us to do. We could compare the two means, that it shifted, it transformed by 100, subtraction by 100. We could talk about how the standard deviation didn't change. There are no real unusuals, that it's both roughly symmetric, and ta-da, we have just cussed and compared. So moving on, here's that wrap-up slide about transformations. This is specifically about adding a constant. Here's a wrap-up slide about just linear transformations in general. It reminds you that we will talk about linear transformations the same way we talk about quantitative data, which you guys know as the acronym CUS. And also, please note that these results both apply to discrete and continuous. So transformations occur in the discrete random variable as well as the continuous random variable. Moving on to part 2, let's talk about combining random variables. Okay, so in a lot of statistics problems, you're not just dealing with a singular event. You might be talking about 2 random variables. So we're going to talk about this tour group again, but this time we know that Pete's Jeep tour, we have Pete's Jeep, but we also have somebody named Aaron. And so if you actually look in the textbook on page 369 and page 370, they give you a little bit more information. They tell you that Pete has a sister named Aaron who lives in another part of the country, and she also lives near a tourist area. So since she was so impressed by Pete's Jeep tours, she decided to join the business and run her own. And so she has Aaron's Adventures that she has her own. And so after a year of steady booking, she comes up with her own probability distribution. And so that's the information that we have ahead of us. So we have defined X as Pete and Y as Aaron, and we've defined T as the addition of X and Y. So we're talking about combining random variables, and so that that T value is going to be our total number of passengers, because X was the number of passengers from Pete, Y is the number of passengers from Aaron, so T is going to be our total. We want to know the mean and the variance of T. Not X, not Y individually, but T, what happens with the total. So if we break down our probability distributions based off of X and Y, based off of Pete and Aaron, we end up with these tables, and we can calculate the mean and we can calculate the standard deviation. But how do I take this information that's broken up as X and broken up as Y and combine them together as a T value? So I do have some formulas for you coming up, but let's just jump on in. What do you notice about how I created the what we would call E of T, the mean of the T value, the expected average or expected outcome of the total of passengers? So what did we do? We just added the averages of both. That's literally all we did. And so here is that formula for the mean of the sum of random variables. So since we're talking about sums in this one, at the very end, I'm going to wrap up about differences. We won't do another example. You can look in the textbook for that, or you can look at my addendum video. I think I might do one that has a difference. But in essence, you're just adding the means. That's it. That's pretty easy. So that's nice and simple. And in fact, I'm going to make a note of it now, and I'll tell you later. On the difference, you will be, guess what? Subtracting that. And, if you kind of guessed that for yourself, great. If you didn't, that's okay, because the second formula might confuse you when we talk about differences. So now that we've discovered that the mean is 6.85 passengers per trip of both tours, then how much variability is there in the total number of passengers? So again, we're talking about variance and variability. They don't necessarily want us to solve for standard deviation yet, but we might need it to interpret or understand what's going on. So the only way to determine the probability of t is if x and y are independent. So we kind of previewed this example, and to solve this, we really have to understand a new definition of what independent random variables are. So you can read this little text box about independent random variables, but in essence, it can x occur alone, can y occur alone. If we think about Pete and Aaron, and I should pull up these next couple of slides, they want you to think about it. Does it seem reasonable? So if Pete and Aaron are in two different parts of the country, does it seem reasonable that these are stand-alone events? Yeah, I know that you might see it as if you're in Pete's tour, you're not in Aaron's. Well, sure, but if you're in Pete's city, you're not in Aaron's city. So does it seem reasonable that these are independent events? Yes. If they were in the same city, you might need a little bit more information, or you might need to reason through it logically why they would be independent events, but you need to come up with one that seems reasonable. It's not, you're making up some sort of randomness. It's a reasonable assumption of independence that you and all the other statistics kids could have come to at the same time. So if you all can come to that same assumption, it's probably a reasonable assumption. If you're the only one thinking on that train of thought, maybe it's not so reasonable. It might not be invalid or inappropriate, but it might not be as reasonable. So it might not be an assumption of independence. Anyway, there's my whole spiel. You have to think through it. That's just what I'm saying, is you got to think through some of these concepts. But if we let t equal x plus y, so we're talking about the sum of random variables, then we have to create this table of all possible combinations. So what do you see here? This is Pete's side, this is Aaron's side. So if Pete had 2 passengers and Aaron had 2 passengers, and we saw there are 2 unique probabilities, okay, well, there is a combination of 0.15 times 0.3. But we could also do the combination of 0.15 times 0.4, or the combination of 0.15 times 0.2, or 0.15 times 0.1. So all of the unique different probability sets that we could create for ourselves and create all of these total number of passengers. And there's where that average of 6 point whatever it was kind of comes from. So if we calculate based off of this t value and this probability value, we can use our variance sigma formula to calculate based off of that t value. So we calculate it and we end up with 2.075. That's the variance of t. Okay, so that's the total variability of t, the random variable we have assigned for the sum of Pete's and Aaron's passenger combinations together. Very quickly, they did the calculations for the variance of x and the variance of y, and they want you to see what do you notice about the variance of t? Did we just add up 1.1875 and 0.89? Is that where we got those from? Could we have just calculated that for ourselves and got that same answer? Okay, and so I just went ahead and did that. 1.1875 plus 0.89 got me 2.0775. So yes, if I had just the variance, and again, I'm saying that word a million times, just the variance of x and just the variance of y, I could have added those together. So I could have also calculated both of those, or if I was given that information, I could have found the variance of t. But I keep saying that word because I want you to read the yellow bolded information. You can add variances of 2 random variables if they are independent, but you cannot add their standard deviation. So either on this slide or in a previous one or in one of our videos, I showcased, we weren't actually adding variance. We squared our variance we were given standard deviation, so we squared our standard deviation to be looking at the variance. Because remember, the square root of the variance is standard deviation. Standard deviation squared is variance, and you can go back and forth. So here's the formula for the variance of the sum of two random independent variables. And so as you can see, so our u of t, our mean was just x, the mean of x and the mean of y. Our variance of t is just the variance of x plus the variance of y. Or you could do your own calculation for variance using, your spreadsheet on your TI Nspire. What happens, though, when we have a difference? So I want you to notice the only major change is the mean. I mentioned it before that if you're summing, then your means just add. Well, if you're differencing, then your means just subtract. But what do you notice about the variance? The variance stays the same. Your variance will still be added together. So please do note that. In general, the variance of two different independent variables will be the sum, whether you're subtracting or adding. Okay. And here's one more wrap up. Okay, yeah, so I think this is the one where we are given standard deviation, so we technically bring it back to variance in order to add them together. So we're given information about Mr. Starnes, and if you want a little bit more information about this particular example in the textbook, it is on page 380. So if you're in the textbook, this is on page 380. And Mr. Starn likes between 8.5 and 9 grams of sugar in his hot tea. Suppose the amount of sugar in a randomly selected packet follows a normal distribution with a mean of 2.17 grams and a standard deviation of 0.08. If he selects 4 packets at random, what is the probability his tea will taste right? Well, that's a heck of a paragraph to read. So I'm going to pause and interpret that for myself, especially the question set. So I see this as if I select 4 packets at random, then if I add up all of their masses, the masses should fall, or not really should, but I want to know the probability that the mass of the 4 packets will be between 8.5 and 9 grams of sugar, because that would make his tea taste just right. So again, I'll say that. I select 4 packets at random. If I add up their 4 masses, then will those 4 masses be between 8.5, the sum, will those 4 masses be between 8.5 and 9 grams? So this is a sum combining random variables example. We did another one, but we're going to do one more, another sum of normal random variables. And the reason why this one's a little bit different is because we are told that it is a normal distribution, so we might need that information to solve this question. So first and foremost, let's do some definitions. We went ahead and used X as a representation of our random variable, and it's going to represent the amount of sugar in a randomly selected packet. And you might say, how is this a combining random variables example? And that's because we don't have just X, we have X sub 1, X sub 2, X sub 3, X sub 4, and each of those is going to represent a randomly selected packet. So in order to find T, the total, we're going to put X sub 1 plus X sub 2 plus X sub 3 plus X sub 4. Where did I figure that out? That's interpreting the paragraph itself. That was that, how do I understand what this question is asking me? I have to create that formula. We want to find the probability that T is between 8.5 and 9, and yes, we can include 8.5 and 9. So we've set up our definition. Now let's do the calculations. What is X sub 1? What is the amount of sugar in a randomly selected packet? Well, they didn't give us any other information except that the mean was 2.17. So guess what X sub 1 equals? 2.17 grams. Guess what X sub 2 equals? 2.17 grams, and so on and so forth. They didn't give us any other information, so we have to use the information at hand. So now I know that the mean is actually 8.68, because remember, when I'm summing random variables, I can just sum all of their unique means, If I was differencing, then I would be subtracting all of their unique means. But so I end up with 8.68. What does that mean? How would I interpret the mean of 8.68? Well, this simply means, we already did, Okay, well, we're not quite there yet. I thought I had a sentence in there, but I don't. But what would this mean? This would mean that there is, if I randomly select 4 sugar packets, there is we more than likely have an average of 8.68 grams in the total combination of packets. That's what that 8.68 represents. So now let's figure out our variability. But again, we weren't given variance of X, we were given standard deviation. So guess what I have to do to those standard deviations to get back my variance? I have to square them. So since each X value is equivalent to, since each X standard deviation is equivalent to 0.08, to get its variance back, I simply do 0.08 squared. So that's just giving you that one more time, where we got these numbers from and why we're using them. So if we add them all together, we end up with the variance of t. If I want to know its standard deviation, there's only one thing left to do, and that's square root it. So now I have the standard deviation of t is 0.16 because I square rooted 0.0256. So I have 3 numbers that I can use to help myself find the probability. We haven't fully solved this because this is the mean, and this is the variance, and this is the standard deviation. We haven't solved the probability. But because they told me it's normal distribution, I can use a normal distribution curve to solve this. So this information started with Chapter 6 information, and it's going to finish with Chapter 2 information, where we did z-score tables and normal distribution and the empirical rule, and we used the back of the textbook, the tables in the back of the textbook to solve it. So we're going to do that. If you need to recall that information from Chapter 2, either watch videos from before, come see me, get a textbook, whatever you've got to do to understand how to finish the solve of a normal distribution. Here's my work. So I drew out a normal distribution curve. 8.68 is my mean because I calculated that for myself. I also calculated the standard deviation. So here's my z of 1. Here's my z of -1. Here's my z of 2. Here's my z of -2. Here's my z3. Here's my z -3. So I created a random distribution, a normal distribution curve. We were told 2 distinct observations, 8.5 and 9. 8.5 and 9. We were told those distinct observations. So I convert them to their z-score, and then using that information, we calculate their probability. So since this is as we approach -1.13, we have a probability of 0.9772, and as we approach 2, we have a probability of 0.1292. So if we get the difference between those, we have a probability under the curve of 0.8480. So if I convert that to percentage, then it's either 84.8 or an 85% chance that 4 randomly selected packets will make Mr. Starnes' tea taste just right. Or there's an 85% chance that if I select 4 packets at random, that his tea will taste right because it will be between 8.5 and 9 grams of sugar. Kind of however you want to wrap up on that. The only thing that's kind of missing from this sentence is that they were randomly selected packets. Okay, so to wrap up for today, for 6.2, again, we talked about transformations. We learned how to calculate the mean and standard deviation when we're talking about sums and differences of independent random variables. And finally, if we have independent random variables, how do we relate that back to our normal distribution curve? All right, that's all I got for you guys.